So we saw how the primordial star formation, the very first stars or population 3 stars, reionized the universe as the first protogalactic fragments form. Let's take a look at this in a little more detail. Here again is the same schematic outline of how things happen, that you start with microwave background release at the age of 300,000 or 400,000 years after the Big Bang. Then dark halos keep forming through what's called dark ages, when the universe is about a few 100 million years old, maybe 500 million years old, the very first stars form. Then through the next few 100 million years, until about the age of 1 billion years, the reionization commences, and it's complete by about the redshift of 6. We can simulate the very first star formation, and this is from one of such simulations by Thomas Bell and his collaborators. And some of these first stars can ionize the gas around them, as well as contribute metals through their explosions. The way we can actually detect reionization era is through the Gunn-Peterson effect that we mentioned earlier when we spoke about intergalactic absorption. This was developed already in the 1960s. It was recognized when quasars were discovered that they can provide excellent probe of intergalactic medium at high redshifts. And if there is even a small amount of neutral hydrogen, it'll be very effective in absorbing radiation blueward of the Lyman alpha line. It will manifest itself as a sudden drop in flux blueward of the Lyman alpha line. And that was finally seen circa 2000. Here is how it works. If you're looking at a quasar that's just inside the reionization era zone, then the line of sight will go through a lot of these bubbles, and the gaps between them will be where neutral hydrogen is, and they'll manifest themselves as a continuum between absorption lines. As you get closer and closer to the reionization itself, the overlaps of the bubbles will be less and less, and there'll be more neutral hydrogen. They'll just absorb large chunks of spectrum blueward of the Lyman alpha of the quasar itself, and the spectrum may look like something like this. And indeed, this was observed in essentially all quasars at about redshift of 6 and above. The same phenomenon was seen. There was a very sudden drop of flux at Lyman alpha line, and then at lower redshifts, then Lyman alpha forest would continue, but then you would run into the Lyman limit that corresponds to the redshift of the quasar, and then flux will be gone again. So this was the most distant quasar for a while, and shows a beautiful example of the Gunn-Peterson effect. So in the face value of it, we have found reionization at about redshift of 6. If you look at transmission of Lyman alpha flux against redshift, the higher redshift you go, the less flux goes through because of Lyman alpha forest. But then by about redshift of 6, there is a just dramatic increase in absorption, which was seen and manifested itself as Gunn-Peterson effect. And this is why people think that that's pretty much when the reionization era ended. You can convert the observed absorption into the opacity of neutral hydrogen, or fraction of the neutral hydrogen, and the sudden drop in transmitted flux maps into a sudden increase in the fraction of neutral hydrogen. But it's enough that only just 1% or so of hydrogen is there to achieve the same effect. There is also variation in different lines of sight. This shows the Lyman alpha forest in the approach to reionization along 4 different lines of sight to 4 different high redshift quasars. We think we understand this because of the biasing, that there'll be substantial cosmic variance, there'll be different large-scale structures, there'll be structures forming at the highest peaks, and that means that there will be actually a certain lumpiness in the reionization. It will not proceed everywhere at exactly the same pace. A new effect that was seen with WMAP satellite that measured fluctuations in the cosmic microwave background was a sudden increase in electron opacity that corresponds to reionization, but this one indicated that it happened around redshift of 10 or 20, which would be substantially higher than what quasar data indicated. Now, the more modern analysis of the microwave background data give us optical depth due to free electrons, which come from ionization of hydrogen, and have a peak of reionization around redshift of 10 or so. It's consistent with an instant reionization, but that's physically not very likely, and most likely we're dealing with an extended period from the formation of the very first stars until the time where all of the ionization bubbles overlapped, and that may have taken from redshift 10 or 20 or maybe slightly higher all the way down to redshift of 6. In terms of actual age, that means from few 100 million years after the Big Bang to close to about 1 billion years after the Big Bang. And even though quasar data by themselves cannot really guarantee that there was a substantial amount of neutral hydrogen, remember only 1% or even fraction of percent is enough to cause the same effect, we have other ways of looking at it. One is counting how many Lyman alpha galaxies are there in any given redshift interval. And we expect that as we get into the region of neutral hydrogen, sufficiently high redshifts, suddenly there'll be a drop in the numbers of Lyman alpha emitters because light will be absorbed by the hydrogen. And that's exactly what is seen. There seems to be a rapid decline in the number density of Lyman alpha galaxies past redshift of 6. Also, in the most distant gamma ray bursts and quasars, we can fit the shape of the absorption that is actually the damped wing of Lyman alpha line, and its shape depends on the amount of neutral hydrogen. So that indicates that there was about 10% of neutral hydrogen by mass or by volume at around redshift of 6. So the universe was not fully neutral, but it was pretty much at the end of that reionization phase then. So combining the data from Lyman alpha galaxies, from quasars, and from microwave background yields a fairly consistent picture that we can see how star formation density in the universe was dropping because galaxies, as we go to higher redshifts, because galaxies were just forming back then. That resulted in change of ionized or neutral hydrogen fraction. It also, as galaxies were being built up, you can infer how much mass was generated in stars. And you can also make predictions of what should have been seen in microwave background measurements, and in fact, that matches the observations. So we now seem to have a reasonably consistent story about formation of first stars and galaxies in that era between redshifts 20, 30 or so, when first stars form, till about redshift of 6 when the reionization is complete. Going even deeper would require a different kind of measurement. Neutral hydrogen, even before any stars are formed, will still be detectable to 21 centimeter line that was used so effectively to map the kinematics of gas in spiral galaxies. And there are theoretical studies of this so that even before first stars are formed, that you can in principle map assembly of baryons in potential wells of future galaxies. And there are radio telescopes and experiments being developed to try to detect precisely this. So far, it's too early to actually expect any detections, but within the next several years or 10 years, everybody thinks that we will actually be able to observe these proto-galaxies before they even made stars using 21 centimeter line of neutral hydrogen. And next, we will finally turn to active galactic nuclei and their role in cosmology and galaxy formation.